Hello everyone. Let's begin today's session with a simple but powerful question. Have you ever watched a speedometer needle on a bike and noticed how quickly it sometimes jumps? That sudden jump is linked to acceleration, how quickly velocity changes with time. Now imagine if we could capture this acceleration over time and put it on a graph. That's exactly what a time acceleration graph is. On the horizontal axis, we take time t, and on the vertical axis, we take acceleration a. According to the definition, acceleration equals change in velocity divided by change in time. That means the product of acceleration and time gives the velocity change. So here's the magical insight. The area under the time acceleration graph directly tells us how much the velocity of the object has changed. As you can see in the diagram, this forms the foundation of our study today. Let's first look at the simple case of uniform acceleration. When an object moves with constant acceleration, the graph is a horizontal line parallel to the time axis. For example, if a car steadily accelerates at 2 meters per second squared, you will see a straight line at the value a equals 2. Between any two times, say t1 and t2, the change in velocity is given by the formula delta v equals a multiplied by delta t, which means acceleration multiplied by time interval. So the shaded rectangle under this straight line represents exactly how much the velocity has increased in that interval. Notice in the figure how the rectangle's area matches the velocity change. Now let's make the connection stronger. From the definition A equals delta V by delta T, if we rearrange, we get delta V equals a multiplied by delta T. On the graph, this is nothing but the rectangular area under the line. Let's say the acceleration is 4 meters per second squared and the time interval is 3 seconds. Then delta V equals 4 multiplied by 3, which comes out to 12 meters per second. This means the velocity of the object has increased by 12 meters per second in just 3 seconds. The diagram makes it so much clearer. The shaded rectangle is not just a shape, it is the measure of velocity gained. Let's now work through a full example together. Suppose a graph shows constant acceleration of 4 meters per second squared between t equals 2 seconds and t equals 5 seconds. The time interval is dt equals 5 minus 2, which is 3 seconds. Now the area of the rectangle is acceleration multiplied by time interval. That is 4 multiplied by 3, which equals 12. So dv equals 12 meters per second. That means the object's velocity increases by 12 meters per second during this 3-second period. Look at the shaded rectangle in the diagram. It directly shows the gain in velocity. Things get more interesting when acceleration itself is not constant. In such a case, the graph is no longer flat but sloping or even curved. For example, if acceleration increases linearly with time, the graph is a straight line rising upwards, like you see in the diagram similar to figure 15. In these cases, the velocity change is still the area under the graph, but the area now forms a triangle or trapezium. For a linearly increasing acceleration, the formula becomes dv equals half multiplied by base multiplied by height. This gives us the velocity change when acceleration is not constant. Let's practice this with a slightly advanced example. Suppose acceleration increases uniformly from 0 to 6 meters per second, squared over a time interval of 4 seconds. On the graph, this is a straight line rising from the origin to the point where t equals 4 and a equals 6. The area under the graph is triangular. Its base is 4 seconds and its height is 6. So dv equals half multiplied by 4 multiplied by 6. That comes out to 12 meters per second. Hence, the velocity of the object increases by 12 meters per second during these 4 seconds. Again, notice how the graph gives us velocity change just by measuring the area. Alright, let's bring everything together. We've learned that while the slope of an acceleration time graph doesn't have much meaning, the area under the graph always equals the velocity change. For constant acceleration, the area is rectangular and dv equals a multiplied by dit. For variable acceleration, the area could be triangular, trapezoidal, or even curved, and velocity change is calculated from that area. And here's the exciting part. This principle is not just theory. Engineers use acceleration time graphs in real life. For example, in crash testing of cars, sensors record acceleration during collisions. From the graph, experts calculate how much the velocity changed during impact, and this helps design airbags and seatbelts that save lives. So to sum up, time acceleration graphs provide a simple but powerful tool to understand how velocity evolves from acceleration. I hope now you feel confident about how acceleration, velocity, and graphs are connected in motion. See you in the next session, where we'll explore another fascinating concept of physics.